This week we are going to start a new tutorial. It's called Combinational Blocks. The digital logic has two different main domains. One is combinational logic, another one is sequential logic. And this tutorial and the report for this tutorial is due next Thursday. And also just remind you, there will be a tutorial report, which is homework tools report, is due this Thursday. Any questions on anything? No? Cool. Okay, before we get into the tutorial, let's review the logic for half adder and full adder really quick. It's been a long time. Half adder. How many inputs, how many outputs? Yep. 0, 0, 0, 1, 1, 0, 1, 1. And the results are 0, no carry out, 1, 1, 0, 1. So here's the truth table, right? So what's this called? Truth table. All right. What's next? So what's the purpose of doing this? Design the digital circuits for the half adder to implement the logic into the hardware, into the real world. So first you need to list all the combinations of the input and get the output, and then write down the, it's called min terms, remember? So where to get started? You should look at each output for each time, because each output has a corresponding circuit associated with it. So let's look at S first. Design the circuit to get S from these two inputs. So we're going to look at the ones. All right. It's going to be A not B or AB not. For CO, there's only one here. It's AB. Okay. And then design the circuit. You have two inputs, A, B. If you forgot how to get these logic equations from this, just go back to the 241's YouTube videos and watch it, all right? So we got A and B. S is A not B, or so we need an inverter here. A not B and AB not and or, so this is S. Is there any problem with it? This is just a XOR gate. Instead of using all these inverters, AND gates, OR gates, I can design a CMOS based XOR gate. So you have taken my digital electronics. If you haven't, you are going to take it in the near future. But just let you guys know, everything here is just an XOR gate. It's XOR logic. Okay. So what is this operator here? And so the circuit can be simplified. We got AB. S is A XOR B, And the carry out is simply A and B. And that's the logic circuit for the half adder. Okay, very quick. Full adder. How many inputs? How many outputs? We're just using the very traditional ripple carry full adder, RCA, A, B, C, I, so 3 inputs, 2 outputs, S, and carry out. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. Still looking at each output each time. So figure out S first. So before you list all the logic equations, you are thinking, I might be able to simplify the logic by doing what? So this is reinforcing the knowledge you have learned in logic. You know, this can be interview questions. These are so fundamental. Okay. So how to simplify this truth table, or how to simplify the logic? You have a truth table, you can list the logic equations by looking at the ones, and you can combine these min terms to make the logic equations. However, sometimes it's difficult to simplify the logic from the logic equations. So what do we want to use to simplify the logic? K-mat. Okay. A, B, C, I, 0, 1 for A, 0, 0, 0, 1. What's next? 1, 1, 1, 0. Keep in mind, only flip 1 bit each time. So what are the ones in here? 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1. It turns out that there's no way to simplify it. Wait, 1, 1, sorry, here. Just directly write them down. So S equals A na B na Ci, A na B Ci not, A B not Ci not, A B Ci. Then what's the next step over here? Combine these two and combine these two. So you can take Ci out. A not B not, or AB, Ci, or A not B not, A not B, or AB not, and Ci not. And because this is A X nor B, and this is A X or B, and also we know that A X nor B equals A X or B not. Just assume you know this. It's given. All right, we derived it in logic. You know, you don't have to re-derive it again, but just know that. Okay, XOR is the inverted signal of XOR. So in that case, we have A XOR B not CI or A XOR B CI not. So this becomes another XOR gate if you treat everything here as one entity. Okay, something not something, or something and something not. Okay, so that's the XOR gate. So this becomes this eventually. So summation for the full adder is literally just the XOR gates, two XOR gates. So what about carry out? So when you are doing your homework for the tutorial, you just do XOR logic, or they just code it up in Verilog. Okay. What about the carry out CO? Still, the K map 01 0001 1110, and the ones are here, 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 here. So the logic equation for C out varies, depends on how you simplify your K map. Okay. If you do this, you are going to get the logic equation we have in the tutorial. So CO equals you have 1, 1. So which one is being toggled? B. So cancel B. So it becomes CI only. Is that correct? It's A, CI. B, CI. And these two. A, B. The CI is toggled, so it's cancelled. So AB left. So this becomes A or B, CI or AB. So this is different. The logic equation can be different if you group them in a different way. Okay, so I think this is a simplest way for CO. But if you just group like one here, and two here, you're getting a different equation. So this is the most popular one. So the logic circuit looks like, so you have AB, so just need one XOR gate, and then CI, another XOR gate, so this is S. So in Verilog, you can create a wire over here, or whatever, it's very simple, just code it up, right? So AX, XOR B, XOR CI, and that's it, I think, in Verilog. Yeah. For CO, so A or B and CI, A or B and CI, or AB, AB. Like that. So this is CO. A quick question. Are you able to create a fast full adder using the AOI logic? If I've taken digital electronics, CMOS level, just the CMOS transistors. Let me show really quick. Do I have it somewhere? I think so. Couldn't find it. Sorry. So something like that. Can we use Verilog to create a circuit like that? Because we are thinking the logic gates are taking too much space on the chip. There's too many transistors in there. Can you simplify the circuit using CMOS logic? In Verilog. I mean, can you build a circuit like that in Verilog? Why? Hmm? No. You don't have the circuit. So Verilog cannot reach that level, that bottom level. It's only handling, so if you look at the operators, these are only like AND or XOR. So these are gate level circuits. So you cannot simplify your circuit down to the CMOS level. Okay, you couldn't touch anything in the CMOS level. Let me give you an example. I have a friend who is a senior engineer in Qualcomm, digital design engineer, designing, probably part of the team designing all the digital circuits, the chips for Qualcomm. However, he knows nothing about transistors. But can still be a senior digital engineer. Just let you know. It's a different layer, okay? Different layer of design. Another thing I want to let you know is decoders, since you have homework assignment on the traffic light designer, a traffic light controller as a combinational logic block. So what is a decoder? Why do we need a decoder? That's a question, I think. For example, the 224 decoder, 224 decoder. Still, it has AB as inputs, and these are outputs. So a standard 224 decoder is like that, 00011011, and only output a 1 for one of the 4 outputs each time. Right, so that's a standard 224 decoder. So you can see the ones are here. However, is this the only option for as a decoder? Yes. So definitely, if you are looking at the examples online in the textbook and everywhere, this is the standard decoder. But sometimes we may need a different logic output combination, not just turning on this bit, only one bit each time. We probably want to turn on, this one for the first code, and then turn on this one for the second one. I mean, does that matter? Can we achieve that as well? So you can definitely get a logic equation from this truth table. That's a standard 224 decoder, but I just want to let you guys know, because you have to design the decoder for your traffic light controller. I think in the lab, I guess. So for example, I need AB as the inputs and CD, EF. So this is just input outputs, input and output, and it's a black box, has 2 inputs and 4 outputs. And these are being connected to anything. It can be an LED light for each of them. Okay, and I need a decoder because I want to reduce the number of pins being used on the circuit, so I can use 2 pins to control 4. Okay, otherwise I have to connect your microcontroller to 4 of them and turning on and off for each of the pins. And so if you have 2 inputs, how many patterns can you create as the output? How many different patterns? Or how many output combinations you can create from this digital block if you only have 2 inputs? 4, right? But you are thinking, I have 4 outputs. 4 outputs can if you are not using 2 inputs, how many different patterns you can create using 4 lines? 16, right? But you are not using all the possible combinations at the 4 outputs. That's why for the decoder, you can see there are only 4 different combinations here. 1, 2, 3, 4. Right? However, these outputs can be any arbitrary combinations you want. Depends on the application. 0, 0, 0, 1, 1, 0, 1, 1. Can I just do 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, like that? Yes, you can. You just fill in all the empty slots over here and look at each output each time, find out the logic equation, and then simplify it, and then draw the circuit. Okay, but when you are designing this in Verilog, do I need to draw the circuit? Do I need to get to here? No, this will be good enough. Just code it up. Then the synthesizer is going to do the job for you. Okay, is this a decoder? Yes, it's decoding. You got a code as an input for the digital block, and it's outputting a pattern for you. Okay. Another question: can you use 2 inputs to output like 6 outputs? Yes, you can. You are not just using all these possible combinations, right? You just need 4 different patterns like this, right? Why not? Can you? So what the circuit looks like? How can you design the circuit to implement this truth table? So it's very simple. If you are not always thinking about the circuit, it's literally just like a password or passcode for the in system. You put that passcode in, and then it's going to output a pattern. You can have 1,000,000 bits here, right? It doesn't matter. So these are all decoders. So for example, for this case, how do you design the circuit? You have to look at each output each time, because each output has a corresponding circuit block to create these ones or zeros over there, right? So I have to look at each one each time. So for the first one, to get C, so for the circuit to get C, that bit, what's the logic equation to use? I have to look at this one, A not, B not, or A, B not, A, B. That's it, okay? Can simplify it. It's A not, B not, or A, B not, or B. What is that? 1. So 1 and A is still A. A, B not, or A is what? Yep. Why? What did you got here? Can't derive it. Let's try it. I couldn't guarantee. I was trying to recall my memory from here. So what if we have this? So it's the same as this one, right? There's not changing anything. And I got a it's going to work or not? We combine these two. No, I couldn't remember how to derive it. Never mind. Nope. So this is just one example to tell you how to get the logic equation from the truth table and simplify it. You don't have to do it here. You can use a K-map to simplify it. So you don't have to do all these derivations. It takes time. It's the same for the traffic light, which is one of the labs on Thursday. Okay, for the lab of this course. There are a few other things I want to let you guys know on the tutorial. So a few of the examples at the very beginning of the tutorial, these are just the adders and multiplexers. Comparators is very straightforward, has all the truth table already listed for you. 4-bit comparator, nothing fancy here. Encoders, it's going backwards. It's looking backwards as a decoder. So I think there's a homework assignment associated with this one. Let's see. So the way to derive the Q0, which is one of the outputs, one of the 3 outputs for the encoder, is already shown here. And you can use this example to guide you through the derivation of Q2 and Q1. So you can find out the final logic equation for Q2 and Q1 for your Verilog design. All right. And there's one thing you probably didn't learn in the past: parity generator and checker. The principle of this functional block is very simple. For example, there are 2 types of parity generators. One is even parity generator, and another one is odd parity generator. And we are only going to work with the even parity generator because they are super similar. And you just need to know one. And this is the one we're going to use for, I think, VGA communication. In a couple of weeks in one of the labs of this class. So the purpose of a parity generator is to get rid of errors during the communication. So how that works, let me show you really quick on the paper. So if the sender, for example, ABC, 3 bits, is sending 001, and if this is an even parity generator, so from the transmitter side, so the generator is for the transmitter side, okay? before the digital data is being sent out, it's going to wrap them up and generate a 1 here to make the number of ones to be even. So that's why it's the even parity generator. So this is the parity bit. And the data only has 3 bits, but however, 4 bits, all the 4 bits will be sent to the receiver. Okay. And then on the receiver side, it has a even parity checker. So it's going to check if there are even number of ones in the package. Check if even number of ones so we can find out this is not 100% guaranteeing the data is correct, because if you have 2 of the bits being flipped, so you are still getting an even number here. This is not 100% sure, but I think to some extent it is able to tell if there are some of the bits are being flipped and sending some errors to the receiver. So for example, the data, so the exact data is 001. Okay, that's the data the transmitter is trying to send to the receiver. So there's a logic block which is called even parity generator. It's going to detect, going to check how many ones are in there, and then generate a 1 or 0 for the parity bit. If there are even number of ones in the original data, here it's going to be 0, like 011, for example, as a data. So the parity bit becomes 0. So it's just trying to make, so the even parity generator is just trying to make the whole package being sent to the receiver has an even number of ones. Okay, so they have the same standard. So the receiver knows it's going to be an even number of ones over there, and then it's going to start checking how many ones are in there. Okay, so for example, during the transmission lines, there are some noises, and creating this bit to be flipped. So this becomes 1. All right, and eventually there are odd number of ones being received by the receiver. So it's going to be able to tell that some of the data are being flipped because of the noise or become to something else. And then it's going to drop that data, not store it into the register, just to not use it. That's how that works. So it's literally just a combinational logic block, and how to implement it, you just need to convert that concept into a truth table. Okay, here is a truth table. It's a 3-bit message and even parity generator bit. You can see that 0 is also an even number, right? So that's why you have even numbers of ones over here. Even, 1, 1, even, right? 1, 1, 0. Okay. So based on the concept, you can generate that truth table, and from the truth table, after you get the truth table, you don't have to think about the problem anymore. Just look at truth table and convert it into the logic equation. So from here, you get a P. So P is a generator, so that's why you need the inputs as a ABC as inputs to the logic block to generate a P. So you can form a 4-bit package and send everything to the receiver. So eventually you can see the logic equation is very, very simple, right? So that's a even parity generator. And for the receiver or checker, even parity checker is on the receiver side. So receiving 4 bits because the sender is sending 4 bits, including the parity bit. And if it's even, then it's going to be 0. If it's odd, you need to set a flag or set that bit to be 1 to indicate there's an error somewhere. Because it's impossible to have even an odd number of 1s in the 4 bits if it's correct, right? If it's an odd number of 1s in there, which means some of the bits are being flipped, being toggled for some reason. So these are error messages. And there's an odd parity generator just for a reference. I don't think we have any homework assignments on that because it's literally the same thing, just doing it in a little bit different way. And there are 2 applications. One is the home alarms system. It's being improved compared to the last one from the last tutorial. And the second one is a car parking spot counting system. And that's it for this week's tutorial. And labs. On Thursday, it's just 7-segment displays, very simple. So, but I think it worth to take a look at the 7-segment display on the board. Is this common cathode or common anode for the display? But looking at this diagram, so you can see that the anodes are being shorted together. All the LEDs, the anodes are being shorted together, but the cathodes are available here for you to send any signal over there. So you have to give a 0 in order to turn on the LED, not 1, 0. You need a 0 for that pin, right? It's the only thing you need to be aware of, I think. You're not building this circuit, right? This is RTX 7 FPGA on the Basic 3 board. It's just showing how these anode activation pins are working with the Samsung display modules. You don't need to look at these ones, right? Just this part. So you can activate each display digit individually by setting this one to this bit to 0. So if you give a 0 here, it's going to allow a current flows through this display module and turn on the whole module. Okay. And we're going to explain the details about this technique. How do you display different characters on each display module individually? Okay, this is the surface problem to think about. But now I think you should be ready to work on the tutorial here, combinational blocks, and I will be around to answer any questions you have. Right?